Good morning, ladies and gentlemen, and welcome to this webinar produced by the SAIEE Nuclear Chapter on nuclear science and technologies at the IAEA, ensuring future energy and water security. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Nuclear Chapter playlist. You will find the registration link in the chat box. Please click on that and register so you will receive a notification when we upload this. Registration is free. A certificate of attendance will be issued a few weeks after this webinar once we've received our validation number from EXA. I'd like to introduce you now to our host this morning, Professor David Nichols, who is the chairman of the SAIEE Nuclear Chapter. He was appointed as the chairperson of the board of the South African Nuclear Energy Corporation in January 2020. Prior to his retirement at the end of December 2018, he was the chief nuclear officer at Eskom. Internationally, Mr. Nichols was the chairman of the IAEA Technical Working Group on Light Water Reactors from 2010 to 2016 and is currently the co-chair of the IAEA Technical Working Group on Nuclear Power Plant Operations. He was a member of WANO's post-Fukushima design review team from 2012 to 2018. Over to you, Prof. Nichols.
Thank you, Minx. I think today's a very interesting webinar because normally we discuss boring stuff like nuclear engineering and power reactors and those things. Today we're very honored, and I'm going to ask you to, can you move the slide forward, Minx? To have Professor Melissa Denneker, who is the director of the IAEA's Division of Physical and Chemical Sciences. And this is the other bit of the IAEA, which is to do with the science side. She was previously scientific director of the Dalton Nuclear Institute at the University of Manchester, United Kingdom, which is the premier nuclear research centre in the UK academically. And she got a series of awards and was previously on the boards of committees such as the UKEA Programme Advisory Committee, the governing board of the Forschungszentrum Karlsruhe, which is the Central Research Centre in Germany, chair of the Scientific Advisory Committee on Canadian Light Source, and so on and so on. I'm not going to go down the whole list. So having said those things, I'm going to ask you to pin your ears back and listen to some intellectuals rather than us clanky engineers talking about the science and with particular view to sustainability in a wide area where the nuclear industry is at work. So with that, I'm going to pass across to Melissa. The floor is yours.
I have to unmute. Thank you very much. Let me start my slideshow. There we go. So now you can see this in the presentation mode, correct?
Yes, perfect.
Okay, and thank you very much. Thank you for the introduction. Thanks you for allowing me to speak today. I'm pleased. I think this came out of a presentation I gave at the African Physics School quite recently, as a matter of fact, and the content's going to be very similar. Because when I look from my vantage point in being in the IAEA and in the United Nations, the two priority areas across the African continent are energy and water, because anything you're going to do requires both. And so this is going to be the central theme of my presentation. My outline is first I will tell you a little bit about the International Atomic Energy Agency and how my division that I lead fits into the landscape there. And then we'll get to the meat of my presentation, talking about isotope hydrology for water security, a little background about energy for the African continent, which I will probably just skip through because you know this better than I do, but then talk about some of the research that is done in my division that is related to nuclear energy. And one is on the back end of fission power generation, and the other is also in my division is fusion research and development. So I have a little video. I hope this works. It's an introductory slide we have. Oops, I gotta find my mouse. Where's my mouse? Here it is. There we go. Can someone tell me if you can hear it?
In 1957, an
Yes, we
agency
can.
was created with a vision to harness the power of the atom for the benefit of humankind. It works with partners across the globe to help countries use nuclear science and technology to meet development challenges, boosting food supplies, improving health, protecting the environment.
Oops. Oops.
And contributing to global peace. This agency provides the technology, expertise, and training to make all this possible. Through nuclear science, it helps countries to develop high-yielding crops that can thrive in extreme conditions, breed healthier livestock, and protect fruit and animals from harmful pests. The work of this agency supports the conservation of our oceans and coastlines, protecting the marine resources that ensure the livelihoods of millions of people. It promotes the use of nuclear technology to fight cancer and improve human health. The organization assists countries with their energy planning. If they choose nuclear power, it offers expertise to ensure facilities are run safely and securely. It provides standards and assistance to ensure the safe use of radioactive materials, guidance on the management of the waste generated by the use of nuclear technologies, and helps nations to prepare for and respond to incidents and emergencies. It's an agency that prevents the spread of nuclear weapons by helping to make sure that nuclear materials remain in peaceful uses. It's the global platform for cooperation in nuclear security, advising countries how to guard against nuclear terrorism and prevent the theft and smuggling of radioactive materials. Providing technology and expertise, promoting safety and security, assisting sustainable development. This is Atoms for Peace and Development. This is the IAEA.
So that was an interesting video that I got from our office for public, what is it, OPIC, Public Information and Communication. And then here you see our Director General, Rafael Marino Gossi. Our strapline is Atoms for Peace and Development. Most people know the IAEA for its work in atoms for peace and safeguards and nuclear security and safety. But we also have a plethora of activities supporting our countries using nuclear technologies for development. We have 176 member states, There's around 2,500 staff working at both in Vienna, is our headquarters, but where I'm sitting now, as you can see at the far right of this slide, the small image are laboratories out in Seibersdorf. It's about 40 kilometers outside. We have regional offices in Toronto and in Tokyo, and of course we have an office in New York, but we also have one in Geneva. We have 6 departments in addition to our 28th floor and our OPIC that I just mentioned, and our legal affairs office and the director general offices. But the 6 departments that are where the people on the ground doing work. Of course, there's management that supports that we can get things done, but nuclear energy, the Department of Safeguards, the Department of Nuclear Safety and Security, Department of Technical Cooperation, and the Department of Nuclear Sciences and Applications, and that's where my division is housed. In our Department of Nuclear Applications, as the central element are the 12 laboratories that we have. 8 of those are located here in Seibersdorf, where I'm sitting. We have another lab in Vienna, and that's the isotope hydrology lab. And that's probably the birth of all lab work that the IAEA did, monitoring for bomb tests, in particular tritium back then, at the end of the 50s when the agency was founded. And we have 3 laboratories, environmental laboratories, concentrating on marine environment in Monaco. So the development areas that we support our member states to achieve are listed here. There are 17 sustainable development goals that were developed a number of years ago in a UN Agenda 2035. And we do not have activities that concern all of them, but the ones at the top that you can see is zero hunger. I have a list on the coming slides that you can probably better see, but good health and well-being, clean water and sanitation, affordable and clean energy, research, innovation, and infrastructure, which is essentially industrial applications other than power generation, climate action, life below water, life on land, and partnering for the goals. Recently, our Director General has started some initiatives that are bundling activities across the agency together with our member states to respond to global challenges. And these new initiatives you can see listed here. One is Zodiac, and that's addressing zoonotic disease. This was started after the COVID pandemic for obvious reasons. Rays of Hope, this is targeting cancer care across the globe, where a gap analysis was done, and now capacity building and installation of infrastructure targeting diagnosis and radiation treatment as the primary areas to help lower income countries to come up to speed to improve health and well-being. The Net Zero Challenge, this is related to energy production with low carbon footprint. And New Tech Plastics, this is using radiation technologies to recycle plastics, to make alternatives to petroleum sourced plastics, and also for monitoring plastics in the ocean. So these are basically microplastics and their impact on the environment. In our Department of Sciences and Applications, here you see again the list of the Sustainable Development Goals are what we call the SDGs that we support. But we have 4 divisions. One is the marine laboratory, so concentrating on environment. One is the center that we run together with the FAO that's located in Rome, the Food and Agriculture Organization. So this is our division for food and agriculture. And then we have a human health division. And in my division of physical and chemical sciences, we address what we divide into programs, our water program, science and industry, and terrestrial environment applications. So you can see I have 4 sections in my division: nuclear data, physics, radiochemistry and radiation technology, and isotope hydrology. And in fact, my division itself, it spans 2 departments. It's not just in nuclear sciences and application, but also in nuclear energy. I have the only division at the moment that is spanning across 2 departments. It means I do everything twice, but then we are also because we're very integral in the things we do in supporting what other departments do. So our data services and our data development serve other departments, including safeguards and nuclear energy, for example. Here you can just see the faces of the people doing the work. I have 3 laboratories in my division. One for nuclear science instrumentation laboratory, the terrestrial environment laboratory, and isotope hydrology laboratory. And that's where I will start. Isotope hydrology for water security. So in a UN study of water security, they had a survey and scored things on a scale from 0 to 100. And all of the African countries scored below 70, except with one exception is Egypt. And a third of those countries have levels of water security that are well below the recommended threshold of 45 on their scale to 100. And this is very worrying because 19 of those countries on the African continent below the threshold are home to 500 million people. So Egypt, Botswana, Gabon, Mauritius, and Tunisia are Africa's 5 top most water secure countries. Somalia, Chad, and Niger are the least water secure countries on the continent. The water stress and water scarcity are very complex issues, and they cross national boundaries. For example, some of the countries that use the most water by volume are not necessarily the countries with the highest water security scores. Managing resource across water basins means coordinating across numerous countries. For example, the largest basin, the Chad Basin in Africa, has parts of 8 different countries in it. That's Niger, Nigeria, Chad, Cameroon, and Central African Republic, Sudan, Algeria, and Libya. So it's quite challenging. And to make it even more challenging, greenhouse gas emissions and associated climate change are aggravating the situation. In the year 2020 and 2021, there were 131 climate change related extreme weather events recorded. 99 floods, 16 extreme storms, 14 droughts, and 2 wildfires. We know that climate change is having its impact. And it's having a high impact across large portions of Africa, although Africa's carbon emissions share is below 3% of the global emissions. So it carries disproportionately high burden of climate change. The surface water or surface fresh water in Africa is very unevenly distributed. And it's mostly due to the variability of rainfall. And the majority of Africa experiences long, dry seasons. And in some places, this exceeds 5 months. And this results, the lack of surface water results in 75% of the population in Africa relying on groundwater. So to understand what isotope hydrology, just some general words about hydrology. It's the area dealing with the science of water. It studies various aspects of water in the hydrological cycle, which you see in the figure shown at the right. It shows schematically the main processes if you think of the water cycle, the life of a water molecule. The major ones in the atmosphere being evaporation, condensation, cloud formation, precipitation, or rain. And there's different sub-areas of hydrology that study different parts of the water cycle. It's like meteorology, the atmosphere, oceanography is oceans, limnology that studies lakes, and the hydrogeology, groundwater. What you see in the figures and numbers are ratios that indicate the generic changes in water isotope ratios associated with the different processes in the water cycle. And that brings us now to isotope hydrology, because you can track these different ratios. This is a special part of hydrology is the science of water isotopes. And this started actually in the late 40s and early 1950s, when people started to study fractionation of stable water isotopes, deuterium and oxygen-18, and the distribution of radioactive isotope of hydrogen and tritium, another one aside from deuterium. And tritium is made in the upper atmosphere, but following the nuclear bomb tests, where large amounts of tritium were added to the atmosphere, in addition to the what's called cosmogenic generation, the ones that occur, that it's generated in the atmosphere. People started studying tritium, and it's a very useful tracer in the water cycle, and we learned a lot about how the water cycle works from this, because you have these tritium tagged water molecules that you can follow. Other isotopes were then included, isotopes of nitrogen and carbon and chlorine and noble gas isotopes. And isotope hydrology is used for studying a number of things. You can study the dynamics of groundwater, and that helps you manage your water. That means when you extract water from your groundwater source, how long does it take to be recharged? Because you know about the recharge rate, the flow, the residence time, and the transport in your groundwater. But it also is used to tell you something about the groundwater quality, so you can track pollution, notably from nitrogen sources, but also you can find some information about climate, about the paleoclimate of the past, about climate change, climate phenomena such as monsoons and the El Nino across the Atlantic. And you can also, and I'm going to show you a short picture, you can use, because living things see water, have water in them, they have markers in them. So you can use this to study animal and insect migration, and use this for animal protection and insect migration, so you can guide if it's pests, using also nuclear techniques for pest reduction, the sterile insect technique. You can predict when is the best time for application. It's also used for forensic science in a similar manner. So this slide is on here just so you know there's resources. There's loads of information on the IAEA water resource page, which is given here, and some older applications on a series that were if you want to study the principles, they're all there in the citation at the top. So targeting drought. This is also a link that you can find some more information. It's going to play.
The global project to track the journeys of specific raindrops is harnessing the power of big data to monitor water supplies for our thirsty planet. Every month, for over 50 years, researchers have gathered rainwater from stations like this in Vienna and hundreds of other sites around the world. The unique isotopic signatures or fingerprints of each rain sample are recorded, and this information is entered into a large online database where it's compared to similar data from surface water to see which raindrops end up in which rivers.
This large amount of data allows researchers to better understand the water cycle. For example, how, when, and where water is recharged. This information is key for managing water resources, especially in the light of climate change.
The datasets and maps are available to download for free and can be used in many ways. For example, in Costa Rica, where they're helping the government identify key locations to protect groundwater so they can target conservation measures and avoid drought.
We now know which areas need special attention. We know how to protect them to ensure water supply for now and the coming decades.
Okay. Yeah. So you learn that we've been collecting data on water isotopes, precipitation isotopes, river isotope, precipitation isotopes in particular for over 60 years. So we have a massive amount of data. And yes, we do use big data, machine learning, and other tools to mine this data to help in predictive purposes. Yes, and also to understand things in the past. So you need this to be able to assess water vulnerability, and we do generate with our other colleagues water vulnerability maps, so you know what areas are of a particular focus you need for your policy and for protection purposes. Yes, we know that countries need to work on their water resilience. The water vulnerability is increasing, especially in Africa. The water quality is declining, groundwater levels are declining, precipitation patterns are changing, there's increased floods and droughts, and this also threatens biodiversity. The impact of water security is on population migration and also on civil infrastructures, industry that needs water, and also on the environment. So this is from the stable isotopes you saw in the video, you find signatures, and so you can follow what she said a raindrop, but the water molecules, statistically, where they were, how they got there, and how long they've been there because of decay. So it's a way of a chronometer. You can infer how long it will last, your resource will last with this information, and calculate the recharge of your water body. The radioactive isotopes give you dynamic information, and it is used in other areas for geodating. So tritium is the heaviest isotope of hydrogen in the environment and is the radioactive component of water. I mentioned it's generated in the atmosphere cosmogenically. It's actually from cosmic rays converting nitrogen-14 to carbon-12 on a tritium atom. And the global average annual tritium generation is 280 grams, and the inventory in the atmosphere is about 4.5 kilograms. Tritium has a half-life of 12.3 years, so you can date water based on its tritium content. If you find no tritium, for example, you can say that water is old on a human time scale. And for old water, or ancient waters, you use other isotopes such as carbon-14 or chlorine-36 or krypton-81 that have longer half-lives. So Our database is accessible to everyone. We've been collecting data for 60 years, and that's on precipitation. And the younger database is the global network on rivers, isotope content in rivers. And the river database includes also polluting constituents, and notably nitrates. And as an example, at the bottom of this figure, you see the tritium levels around the world. The contemporary average tritium levels around the world in tritium units. Tritium units is unique to isotope hydrology, but 1 tritium unit means there's 1 atom of tritium per 10 to the 18th molecules of water. Historically, this has evolved, but people talk about tritium units. There's nothing to do with Avogadro's number. But you can use these for altered trace analyses. And we do a lot of work in the lab optimizing the analytical procedures and the instrumentation to do this, including some very fancy mass spectrometry quantification of the tritium decay daughter, which is, and we could talk about daughter. Nowadays, people don't want to say daughter and mothers and isotopes because it should be gender neutral. So I will say progeny, helium-3, and this is a very sensitive technique, but it's not an easy one. So I told you that we had an average global concentration of tritium. You can see from this map that the generation is not even across the globe, otherwise you wouldn't have these different areas. The generation in the atmosphere is dependent on latitude, with higher latitudes having 7 times higher rates than at the equator. It's also dependent on the density of the atmosphere, and this exponentially decreases with increasing altitude above the Earth's surface, so in high mountains, yes. So this kind of information you can use to figure out where water comes from. So I'm going to walk you through this so you'll understand this. You see this plot. It is the plot of the local meteoric water line. It's just a line put through all these data points, yes? It's plot of oxygen 18 versus the delta oxygen 18 versus the delta deuterium for the data shown in the table at the top. And the table at the top is just a screenshot up from the database. So the delta is there because the delta expresses that it's a ratio. So for delta oxygen 18, it's the ratio of heavy to light water to light oxygen isotopes relative to a standard, yeah. And that's where the standard that is used is called the Vienna Standard Average Seawater, VSMOV. It's very famous. It's from Vienna, so you can guess where it came from, where I'm sitting near Vienna today. And the delta for the hydrogen values is the analogous value for the ratio of deuterium to hydrogen isotopes. So this line describes the global annual average relationship between these 2 isotopes, yes? And if you observe differences between the local and the global line, there's a global line, it indicates differences in temperature, latitude, continentality, because that has to do with rain, and humidity. They all play a role. And then you can, so it contains information about the climate of the site. And the variations are caused by fractionation of the heavy and light isotopes based on where they are. Because it's dependent on climate, the isotope fractionation processes in the water cycle, there are ways to use oxygen 18 and oxygen 17 data, yes? So you can use this as oxygen 17 as a proxy for humidity, and some of the hydrogen isotopes as a proxy for temperature. So you can start to detangle the climate reconstruction, so you can identify changes and trends. And there's a I won't mention that, it's getting too complicated, but because of those dependencies, you can start to detangle things with temperature and humidity. So this is an application specific to the Sahel in Africa. So to give you a flavor of how isotope hydrology supports management of water resource, the Sahel receives little annual precipitation. And it's indicated in the map highlighted in light green. It's a bit confusing as some of the aquifer basins are overlaid in color. So the Chad Basin in green and the Taco Gorma Basin is in pink. And the blue areas indicate areas that receive 4 times greater precipitation or even more. So because of this, one would expect more recharge of the underlying groundwater in these blue areas because they get more precipitation. However, the study of the groundwater found some surprising results. We find more groundwater recharged identified by young groundwater ages from the tritium measurements, and they're indicated here as dark squares. And these were in samples collected in areas receiving less precipitation. So the darker the square, the larger the young water component in the groundwater. And you can see a cluster at the area at the edge of the basin colored in red-orange of these, it looks sort of like a cross. And this is in areas that have little precipitation. So replenishment or recharge is more resilient in this area. Yeah, so it's more resilient for overexploitation in these spots because they have the youngest waters. And this can help direct policy of your water extraction. Note from this map, you can see that water resources are transboundary issues that I mentioned before. Water quality management. I mentioned that we also look at the water quality. Knowing the quantity is not enough. If it's not drinking quality, then it's not, you can use it for some applications, but you can't use it for drinking. And regulation of drinking water is different than water used for agricultural practices, for example, irrigation, which is probably the biggest water user. So in this study, you see results from a study done in the Taco Gorma system, where they looked at the amount of salt and nitrate in the groundwater. And you can see results for Niger, Benin, and Nigeria in the maps. And the very top map is for water salinity, and the one at the bottom is for nitrate concentration. The size of the circle is where the sampling was done, and its size indicates the level of salinity or nitrate concentration. And what we found in this study, that in boreholes that were they were not being protected by animal husbandry practices, we found a huge nitrogen signatures of nitrogen 15 and oxygen 18 that we could identify their source. And this is the advantage of looking at isotopes. So you can differentiate between natural and inorganic fertilizer. So the nitrates come from fertilizers, but this can be animal dung or inorganic fertilizers put on fields. And in this case, we were able to differentiate it between dung and inorganic fertilizer. So then it's an easy thing is to protect those extraction points from keeping cows. It's as simple as that. I mentioned there's other applications, and here you see for forensics and for biodiversity protection, in this particular example for bird migrations. So if you have endangered or lower species, you can track where they go using the water signatures of the animals. Birds, when elephants, you can observe birds, they fly around, and so you can find exactly where they go and protect those areas. So something new that's going on is I try to show you that climate change is redistributing water around the globe, different precipitation patterns, and some areas are becoming drier and some are becoming wetter. And the way water is received is changing. We have these more extreme events going on. And on top of, convoluted with this, on top of this, the world's water resources are under increasing pressure, both from increasing population, but also from pollution and contamination. And so what we need, we have a lot of data, but we do have some data gaps. And so we are establishing what is called the GLOWAL network. It's the IAEA Global Water Analysis Laboratory Network to fill in those data gaps. Especially to meet pressures, groundwater is, you see this in Africa already, is used as an adaptation mechanism to address climate change and lack of surface water. So you really have to be sure of how you're using your groundwater and manage it properly. So in July, there's a symposium that might be interest. You can join. There's online attendance, and there will be more information about this network at the symposium in July that you see on the left of the slide. And then also of interest, it might be interesting, is the IAEA has some programs for PhD students. These are sandwich programs. The sandwich being you work at your home institution, and then you spend in the middle, usually in the middle of your PhD in a host co-supervising institution, and then you go back home. If you want more information, I can help direct you to our TC department that does this. There are other sandwich specifically for physics via the ICTP program also. So water everywhere, but you also need water to cool your power plants. But then you need power. So here, the future nuclear energy in the African continent. And these are things that I will just go through quickly because I said you probably know these better than I. In the African Agenda 2063, the continent's development agenda, and it aims to transform Africa's infrastructure, economy, and social well-being, and includes energy infrastructure development. Yes, development needs energy, but over 40% of the people living in Africa have no access to electricity. And those with it are often in a precarious situation. For example, I'm sure all of you here know about the load shedding in South Africa over the next 2 years, which leaves people intermittently without electricity. Here you see a map of, it's a different rendition of the access to energy, but 14 countries, African countries, are considering nuclear power generation. Algeria, Egypt, Ethiopia, Ghana, Kenya, Morocco, Niger, Nigeria, Senegal, South Africa, Sudan, Tunisia, Uganda, and Zambia. South Africa already has nuclear power, but is considering another plant. These countries are at various stages. Egypt is currently the only country to have begun construction and has approval for a second unit. They received at the end of last year, I think it was November. It's a 30 billion project delivered by Rosatom, with a total installed capacity of 4.8 gigawatts. Kenya has already identified sites, and there are 2 coastal sites. last year for their first nuclear power plant. This responsibility lies with Kenya's Nuclear Power and Energy Agency. And South Africa's Koopberg Nuclear Power Station is the only nuclear power plant on the continent at the moment, and it has an installed capacity of 1.9 megawatts. But my information is South Africa is considering an additional 10,000 megawatt in nuclear power capacity, but not all at once. So why nuclear? And it's all has to do with the Paris Agreement and reducing greenhouse gas emissions. So the Paris Agreement, to achieve there's two scenarios, a 1.5 degree limit and a 2 degree limit. But for the 1.5 degree limit, which is to be, according to the Paris Agreement, emissions need to be reduced by 45% by 2030 to reach net zero by 2050. So what we need is 13.75 gigatons CO2 per year saving per year for the next 80 years up to 2010. In order to achieve this, we need to use all the technologies with a low carbon footprint that we have at our disposal. This is clear, and this includes nuclear. And for this reason, the EU declared a new taxonomy of low carbon energy sources to include nuclear just this past year. Otherwise, they're not going to make their emission reductions. Here you see there's a roadmap to net zero. You can have a look at that if you haven't already. It has a lot of challenges to get there, and the entire supply chain, not just an installation of capacity. But there's also other reasons for nuclear beyond low carbon electric. It can support the integration of a large share of renewables and ensures security of supply. But it can also help decarbonize some industrial processes, for example, by having cogeneration of hydrogen and using process heat. But there's other reasons. One has to do with pollution. So on this slide is what the World Health Organization estimated in 2016 that 4.2 million premature deaths worldwide per year are caused by air pollution. And a more recent study in the Lancet, this medical journal, cited 6.5 million as a number of deaths. I think this was last year. And this is one of the drivers that China has to increase their portion of nuclear energy generation in their energy mix. It's to reduce its pollution problem. So I come originally from the back end of the fuel cycle, and also from Europe, and one of the limiting areas is the back end. What about the waste? Everyone asks about the waste, and my answer always is waste is the relative burden. There's a lot of other waste that I worry more about than nuclear waste. However, nuclear waste has to be disposed of in a safe and in a long-term safe manner. So you can see the comparison between municipal waste and in volumes here. But there's things about nuclear waste is it's radioactive. Yes, so you have to know what your inventory is, so you know how to dispose of it safely. You have to be able to characterize it in the waste streams. You should be able to minimize the waste this is general in waste management, is minimize waste generation, recycle and reuse, use low activation materials, and mixed waste account for non-radiological hazards and limitations. Mixed wastes are always a challenge, and you need a disposal pathway for radioactive and other hazardous waste. So the research that is done in my division, I have two examples to show to you today. One is using accelerators for waste research and development, because in our physics department, we have a project on accelerators and neutron sources, and also for non-destructive testing for waste characterization. Yeah, so this is the research and development part, and also for the characterization part, which is one of the important challenges. So damage from decay in high-level nuclear waste forms is something that one has to think about at the stability of your waste form. Typically, it's going to be a glass or ceramic for a high-level waste. Yes? If the decay leads to energetic particles, and these energetic particles can cause atom scale defects from ballistic collisions. It means they displace atoms. It leads to a cascade of damage. Also, the progeny of decay introduce new chemical elements into the matrix, and it can destabilize the matrix. So what we have had is a couple of coordinated research projects. This is one of the tools that the agency has to deliver its mandate. It's coordinated research project because we get a number of member states, institutions and laboratories from member states together to work on a project, and we've had a number of projects. The one is called Inward, and it's for ion beam irradiation for high-level nuclear waste development, and it's actually to study that decay, self-irradiation damage in proposed waste matrices. It's to simulate the long-term damage, but you can do it on a short laboratory scale using an ion beam. So you can go up to high DPAs faster than waiting around for a long time. Yes? So it was studied in the waste. They added different actinide elements, which are the long-lived components of high-level nuclear waste, or the largest long-lived components in high-level nuclear waste. And then they studied the waste form with the actinide in it, and compared with different irradiation using different ion irradiation, different matrices. This were done ceramics and glass, and then characterizing them afterwards for leaching behavior. So are radioactive elements released over time, if they're in contact with water, and characterizing with a range of different techniques. What they found was that the ion beams actually can be used to achieve high doses, or high DPAs, displacements per atom, that you can't do otherwise, and they can do this in controlled irradiation conditions, so you can study individual effects. You can use this to develop and validate models. And then they use from alpha decay by using helium as your ion beam. They found in glass there's a transfer of energy to the atomic nuclei in the glass, is primarily by ballistic processes and elastic collisions. And the lower energy alpha recoil particles account for most of the total number of displacements. Yes? So the original ballistic is not responsible for the largest number of displacements. The alpha recoils lose nearly all of their energy in elastic collisions over a very short range and producing localized damage. So these things go on to have studies of the effects on its tensile strength, and most importantly, its resistance to leaching, which is in a repository, a back-end scenario with water intrusion, the most important event in terms of risk. These samples were characterized using X-ray fluorescence at the Electra light source. So one of the things that we do in our accelerator sub-program in the division is we facilitate access for our member states to use the Electra beamline. We have a joint beamline there since 2013. Electra is planning to move towards also a diffraction limited machine in the future, and we will continue. The decision has been made to continue that collaboration as we move forward. The ion beam we used is in Zagreb at a facility called RBI, and we have a very long-standing collaboration with them, and we also facilitate access to their facilities for a number of years. So those are small projects. Another thing you can do is to study large areas. Let's say you want to put a repository somewhere, or you want to characterize waste, but you can't access it. You can use some different non-destructive techniques. And one for waste characterization is potentially you can use this muon radiography. It's an emergency technique, and the beauty of it is it uses a natural source, the background radiation of cosmic ray muons. So terrestrial cosmic ray muons are created when high energy primary cosmic rays interact with the atmosphere, and they produce muons, and they're quite energetic. So muons have properties like electrons, but they have a much larger mass. They're around 10,000 times energetic as a typical X-ray, and release energy mainly via ionization. Because they're very energetic, they can penetrate large structures. And because they're charged, they leave ionization trails as they lose their energy. And so you can detect them. Now, scintillation and ionization detectors and measure their tracks. The huge advantage of muon scattering or absorption techniques is you can detect density variations of high atomic number materials in a closed volume, even if these materials are embedded in something. So for characterization of waste, this makes this a non-invasive, non-destructive technique without needs for an external source. It's obviously benefits for characterizing waste packages. In muon radiography, you need at least 2 detector planes to define where the tracks are coming from, and often use 3 or 4 to increase your resolution and efficiency. What else? Other applications you can think of other than nuclear waste package characterization, you can find all over. Some of them are in the slide. You can use them for studying volcanism. It's very important, tracking where magma is. It's done to a kilometer depth, has been done. And it was used, I think in the next slide, there's a link here at the right of the slide. It was used to study pyramids, where they found some undiscovered places in pyramids that they later went in to look at. So here's you see an example in Los Alamos where they used a mock setup of fuel rods, where you see the cross section through where some rods were in place and some not. And you can see from the reconstruction cross section shown, or line scan shown below, that you are able to identify where the voids are and where the fuel is located. So this was a demonstration experiment done in Los Alamos. Yes. If you want to control the mass of the material inside the package, you need other measurements, yeah, such as photofission delayed neutrons. So you can quantify the mass of fissile material. But here, at least you know where your fuel is in a larger construct. Here, a transport container. So, in that link here at the right, we also have a new publication about muon radiography that you can find in the link. Yes, that's an article, and it's a comprehensive publication that you might find further information. So, what might the future look like? And a comment in the beginning, in a dry run to this event, was fusion has been on the horizon 50 years ahead for us for at least 50 years. And I would agree, this is something in the course of my career. But there's hope for fusion energy research. And there are some advancements that have been made in recent advancements and recent investment from the public sector that maybe are transporting fusion to a faster reality than what we've been used to in the past. Fusion is a low energy carbon source. Let's see if I can get this. This is another little video. Let's see.
Providing energy from nuclear fusion is widely regarded as the grand engineering challenge of the 21st century. Unlike fission, where the atom is split to produce energy, in fusion, two lighter atomic nuclei are merged to form a heavier nucleus. This is how stars transmute matter into energy, and this is the main goal of plasma physics research. An international experimental fusion reactor under construction in France, ITER, is aimed at demonstrating that fusion power can generate energy. The IAEA has played a key role for ITER's creation and its endeavours. To make fusion power commercially viable, a number of serious technological challenges will have to be overcome. A plasma with temperatures exceeding 100 million degrees Celsius, 10 times higher than in the core of the Sun, has to be confined and controlled using the largest magnetic fields ever produced. Finding the right materials and the mechanism that will extract and convert the enormous amount of energy are also among the major challenges in producing electricity from fusion. Through various international cooperation activities, the IAEA promotes innovation that leads to more efficient and affordable nuclear technologies.
There we go. Yes. The benefits is it's a potential source of inexhaustible energy without CO2 emissions and without generation of long-lived waste. However, it does generate waste. We have to be serious and holistic in our thinking. No fusion machine exists that you can put electricity on the grid, not yet. And there are a number of challenges. This slide shows the differences between fusion and fission. Fusion and fission, when you fuse nuclei together. Deuterium, tritium is what is envisioned. And fission, you break them apart. Both you gain energy. Yes. The balance of plant has different challenges. You have at the upper right is supposed to exemplify the fuel is different, but also the waste is different. Yes. But why would you develop fusion if fission is working? Why, if there's challenges, why would you invest the effort if fusion is really difficult? And it has fusion does have a number of merits that make it attractive. It's, of course, yeah, I mentioned low carbon source. It is, but that's an advantage of fission also. Fusion generates low-level manageable waste. Fusion fuel isotopes of hydrogen that you can easily find, and tritium can be generated or bred while in operation, though we still don't know how. There isn't a breeding concept that has been tested in operation, and fusion energy is safe because it involves no chain reaction. The difficult thing, because what makes it safe also makes it difficult to keep the reaction going. Yes, but it's safe. The reaction will stop if the machine switches off. So you can't have something like 3 Mile Island or Chernobyl happen. Another merit is it's a reliable energy source, as is fission, both. So the idea of fusion is it's what powers the sun and the stars. And this was speculated in 1920 by a man named Eddington. The sun is a deuterium fusion reaction. And what is going to be used in ITER and most everywhere are the isotopes of hydrogen, of deuterium and tritium. You force them together at extreme speed and they form products that you see on the right-hand side. It's helium, but also a neutron and a bunch of energy. The difference in mass is where we get the energy. In fact, 4 times more energy per fuel mass is released from fusion than in fission, and 4 million times more than coal, oil, or other fossil fuels. So I said deuterium, tritium is a reaction that other reactions could work, such as the fusion of a proton and a beryllium-11 nucleus. However, there's issues with this reaction, as the power density of this reaction is orders of magnitude lower, and what's called the fusion triple product minimum is too high. And the triple product is the product between the plasma density, the energy confinement time, which is a measure of the rate which the system loses energy to the environment, yes? And that lost energy is mainly Bremsstrahlung, multiplied with the plasma temperature. And the sweet spot for this triple point is where a plot of temperature is at a minimum. It's the triple point is where the Lawson criterion is filled. I'll show you an example. And that's why the most favored fusion reaction is deuterium-tritium. because it has the lowest temperature. Its sweet spot is by 4.3 kiloelectron volts. And that's where fusion self-heating power just balances the losses. Yeah? As I said, mostly from Bremsstrahlung. Here you see the plot of a fusion triple product versus temperature for experiments performed at a number of different facilities. And ignition is where the self-heating overpowers what energy loss or whatever plasma cooling mechanisms there are. Q is the ratio between the power generated by a fusion to externally provided heating power. So that Q, when it's 1, this is scientific break even. This is referred to as QDT or QSCI, and it's not the same as Q engineering, which you might be more familiar with, which is the ratio of electrical power produced to the electrical power consumed. Yes. The International ITER facility that is being built in Cadarache, France, is designed for a QDT of around 10, but its Q engineering will be around 0.7. It is not going to produce electrical power. It is there. It is the E is an experiment. Yes, the E in TITER is for experiment, and I'll tell you more in just a minute. But you see here some different facilities that something happened, and one is JET. JET is now ended its lifetime. It was in the UK, and it was the first tokamak that performed experiments using actual DT fuel, and it holds the record for the highest sustained energy pulse generated for DT fuel. There's a new for DT fuel done in China, I believe, but for this, they had a record-breaking 59 megajoules of sustained fusion energy for 5 seconds. You may have heard of the National Ignition Facility, NIF, that you see here in the insert. A picture taken from a science article when just after it was announced that in December last year that they achieved ignition from 2.05 megajoules of laser light that they directed onto a capsule containing the fuel. They generated 3.15 megajoules of energy. And I will talk about inertial fusion in just a second. So there's ITER and NIF are two different kinds of fusion facilities. So you can see NIF here. They had one in August, and then they reached above ignition. Here's my pointer here. Can you see my pointer? I don't know. There should be a new star above the sweet spot. So the first thing you need to do is make a plasma. And I think you know what a plasma is. You need high temperatures, really high temperatures. To have fusion happen, you need a dense plasma. And that density and high temperatures is to overcome the repulsive forces between the nuclei. So the sun has temperatures above 10 million degrees, and gravity confines its plasma. And to do this on Earth, we need high temperatures 10 times greater than the sun, and have to confine the plasma. And confining it, you can do a number of ways. You can do it with magnetic fields, because the plasma has negative and positively charged particles in it. You can use a magnetic field to confine the plasma, and the most common design is a tokamak. The first tokamak was built in 1958, and it is presently the most advanced concept. Tokamak is it looks like a donut. It's an axisymmetric design with the colloidal field created by a toroidal electric current. And the TACAMAC, its acronym comes from toroidal magnetic chamber. So it sort of names its design. The idea is you create a current in the plasma from an electric field induced by a solenoid transformer, and the plasma current in turn generates a colloidal magnetic field that bends the plasma current into a circle. Yes, and so this is all done inside of a donut-shaped vessel. The other magnetic fields going around the length of the donut are referred to as toroidal, and the combination of the toroidal and the colloidal magnetic fields creates a three-dimensional field shaped like a helix. And these are indicated by black lines in the image at the top left of the slide here, you see. This design is simple, but susceptible to current instabilities and difficult to operate in a steady state, which you need for generating electricity. Or generating heat to make electricity. The current record for steady state operation is held by China. And a year ago, they had announced a steady state. They haven't one more recently. I forget what it is. I think it was like a half an hour or something. Another design for magnetic confinement is called a stellarator, and this has a non-planar magnetic axis. And this is, in such a design, you don't need a strong current in the plasma, so it is less susceptible to instabilities, but they're much harder to design and to operate. The largest one currently is the Wendelstein 7X stellarator in Germany, and it is designed to generate constant and stable high density plasmas for 30 minutes. This design is also not conducive to having a breeder blanket to generate more fuel, more tritium. Although a stellarator is easier to operate in a steady state, it has that and some other challenges. Another way to make fusion is called inertial fusion. And an inertial confinement normally uses high-powered lasers that are directed towards very small cylinders that are referred to as Hohlraum, which comes from the German for empty space. And the Hohlraum contains the fusion fuel, and the lasers are used to heat them up, where they eventually implode and explode. That's causing a pressure and enough heat to create densities necessary for fusion. By compressing and heating so quickly, the fuel burns before it has time to escape, meaning you don't need an extra confinement. Yes? So for energy production, in a system that would introduce a fuel-loaded Hohlraum, or these little cylinders, and successfully ignite each of these in very rapid succession, still has to be developed. What has been done is the experiment in NIF, where they reached ignition. However, that was just the laser heat reading the Hohlraum. It is ignoring all of the energy needed to power those lasers. So it's sort of ignition if you forget about all the other energy involved. There is one advantage of this design that I mentioned earlier is a different fuel. It's a proton boron 11. Boron 11 makes up about 80% of all the boron found in nature, and it's readily available. And so you don't have to breed it. It is not radioactive itself, and the fusion reaction, importantly, produces no neutrons. But you have to have shielding and stop. So in this design, you don't need that. In a magnetic confinement design, you need materials that have to deal with the temperatures that are much higher, and you couldn't do a proton boron it would be very, very challenging. So there are also some other open designs that I will just mention for completeness. Here you see a generic tokamak DT fusion device for power generation. The equipment to the right is similar to a fission plant. It converts the thermal to electrical energy for distribution to the grid. On the first wall of the torus closest to the fusion power core that's where huge temperature and radiation gradients are. And this is a materials challenge. Another challenge is the tritium you need for the fuel. You have to generate by breeding. I told you you make 320 grams a year in the upper atmosphere. You need around 100 grams of tritium per day for an 8 megawatt fusion reactor, or around 300 kilograms per year. Yes, there's only 4.5 kilogram in all of the atmosphere right now. So obviously you need to breed fuel. You can use the neutrons generated in the fusion reaction, thermalize those to match the cross section of lithium nuclei, tritium plus alpha particles, and a neutron, if lithium-7, the reaction with lithium-7, you see here shown in parentheses. What you use is lithium-6. And lithium-6 is the cross section is much lower versus 7, but it does go. You want to use lithium-6, so you need enriched materials. Yes, so that's another challenge. The blanket also, you're making these neutrons, so you have to shield them. The blanket is not only for breeding with the neutron and lithium-6, but it's also for serving as a shield for protecting outer components. It also is the area for heat exchange that is shown here. Yes, the blanket coolant is the primary loop of your circuit to convert the thermal generated from your fusion reaction into useful power. So no large-scale breeding systems have yet been tested. There are some designs that will be tested in ITER when ITER becomes operational. However, validation of the technology will have to happen in what comes after ITER, which is referred to as a demonstration fusion power plant, often called a demo. And demo will be close in design to an actual power plant. ITER is an experiment. So you see the exhaust pumping and separation. So the diverter is an exhaust system, where one, to get rid of heat, but you have to get rid of the helium you're generating. So if the reaction above, you're making helium, but you're making helium and you're making helium in the fusion reaction itself between deuterium and tritium. You have to get rid of it in your plasma. And there's been various designs that have been proposed and tested to get rid of the helium. There's also ablative material, because all the heat, something hitting the wall, you're going to have things ablate material. And the most current advanced design is called a Super X, and it's called Super X because it's using superconducting magnets, and they allow stronger fields and higher confinement, which is good. And it's been tested just recently, demonstrated with a record 20 Tesla magnetic field by MIT Plasma Science and Fusion Center, together with a private company called Commonwealth Fusion Systems. Here you see ITER. It's an experiment. It's a proof of principle. Remember, from the reaction from DT fusion, you generate a helium and you generate a neutron. Most of the energy is associated in the plasma with the helium. This creates more heat through collisions in the burning plasma. The rest of the energy, the 400 megawatts, 80% of the energy comes out with the neutrons. This is one of the big challenges that you have. ITER has another big challenge, is that they found, oh, here you can see the construction, I think in the next slide. Yes, here's a photo and construction. And you can see the tokamak building that is going up. This is an older building. It's coming out of the ground in the left in the center, and it will be 80 meters tall when it's done, with 150,000 cubic meters of concrete and 7,500 tons of steel. It is a huge project. But one of the challenges they have, here you see their timeline. They're now working on a new baseline in terms of time, but also in money. The goal for ITER is to use DT fuel to generate 500 megawatts for 400 seconds. But in construction, they found stress corrosion cracking in a component of the vacuum vessel thermal shield. And now they're trying to figure out what to do if they have to remove them, which is going to be a big feat, to redesign them and remake them. So this is why they're working on a new baseline. Like I said, it's an experiment and has many challenges. And this is a stress corrosion cracking before it's gone into operation. It's a good thing they found these things now. The next step demo will demonstrate self-sufficiency and net electrical output. And this is expected in around 2050, so after 2050. So the fusion research and development has been part of IAEA activities from the beginning. The second general conference of the IAEA, it was called something else at the time, but it was in 1959. And that's when fusion activities became declassified in different countries and they could be discussed openly. Later, the idea for ITER was also born out of fusion activities at the IAEA, and the agreement for the establishment of ITER itself was done in Paris in 2006. And the IAEA Director General is the depository for the agreement that was signed at that time. So the fusion activities is increasing across the House. We have increasing input from safety and security and our nuclear energy departments, in addition to activities that were in my division. So there's a cross-departmental committee that set up in the year I started at the agency in 2019 for coordination of these fusion activities across what we call the House. Our House is the agency. And you can see all the things that we are doing in fusion activities here. We are advised by the International Fusion Research Council on what we do. In this list, I forgot to add, we have partnerships, targeted partnerships to help us in delivery of our fusion program, and one with the Princeton Plasma Physics Lab, and we also have a collaborating center on nuclear fusion research. If you're interested in as a go-to source on fusion devices, you can find it at what's called the FuseDIS portal, and the link you see on the slide. And on this map is different fusion machines, and if you click on it, you can find out more information. And so it is an international endeavor, and the challenges faced by fusion to become a reality cannot be solved in any singular national program, and concerted international effort is obviously needed. And that's a role that the agency plays. And every 2 years, we get the fusion community together to the Fusion Energy Conference. The next one is coming up in October in London, the 16th to 21st of October in London. And I invite you to join us there. And that's an abrupt stop, but I think I'm also pretty much out of time. Yes, I'm very sorry.
Thank you very much indeed, President Denica. People are not yet questions here. Oh, there are some questions in here. Good. Let's see if I can get this out. Before you start, I just want a couple of comments. Two things of interest, just for interest for the audience, essentially, that one of the interesting facts about the Falput site in the Northern Cape, which is the low-level waste disposal site for South Africa, is that these water techniques that Professor Denica was so well discussing were used to establish that the water table, which is well below the repository, I think has got a situation of the water was last recharged about 20,000 years ago. So there is no movement of water through that ground. That's the kind of thing that's being done with that in the pure nuclear area. And I'm going to ask a quick question, and then I'll look at what's in the box. I've got a question from Simon Cannell. Welcome, Simon. He may have moved on, because I know Simon was having to leave the meeting early to travel, but I'll ask his question for him. But the first question is, in those tritium levels across the world, to what extent has the bomb testing impacted those distributions? You mentioned that the altitude both the latitude and the altitude affected it. To what extent is the bomb testing from the 60s, 50s, 60s still affecting the tritium levels in the world?
Okay, that's a really easy one to answer. It doesn't, because the half-life is 12 years. We're more than 7 years, 7 times the half-life. So it's essentially, we're back to the levels that are for cosmogenic generation. And this is what is making it exceedingly challenging for us. We're doing all kinds of things of trying to extract tritium from samples to concentrate it to reach the low levels that we have to do. Also using looking at progeny by letting samples sit around and then looking at the daughters for helium, because the helium daughters, they're heavier, and we do it by mass spectrometry. Yeah, it's called the ingrowth technique. But at the moment, it's pretty much gone.
Good. I also must comment, the idea that we shouldn't call them daughter products because of this insane wokeness in the world strikes me as horrifying, but I'm probably going to get cancelled for even mentioning that. I had not heard of progeny before. I know what the word means, but I hadn't heard it being used in this context. I'd assumed that daughter products were allowed to be used because they're real.
Yes, but I think that suggestion came from the Bureau International Poids Mesure, and they would have a say in this. And there is I don't think there's anything official, but there is a movement to get away from mothers and daughters and talking about progeny. And I'm trying to be politically correct. And yes, yeah, I have to change my lingo because I started out with daughters. Interesting, you mentioned the water below a repository. I would like to comment just on that, because one of the reasons I got my job, I come from the back end research actually originally, And one of the reasons I got my job is because isotope hydrology, my experience came from looking at water dating around repositories, because this is something that you do, and you want very old water. If you want water that you're going to extract for use, you tend to want younger waters or a huge reservoir of old water that you can, yeah, you can tap into. But yes, this is true. This is a typical application of isotope hydrology in waste repository characterization.
Yeah, it's well, just talking of our repository, what's interesting is that we have 100 square kilometers size repository. Someone was complaining about have we got enough space in South Africa to dispose of our nuclear waste, and the size of the Falputz repository is 100 square kilometers, which I think may be one of the biggest repositories in the world in that sense. We use about 1% of it at the moment. I just read out the question for Simon, who then had to depart, he's traveling. For Africa to benefit more fully from nuclear energy, we need to address the issue of regulation. It takes decades to develop a national regulator. SMRs could potentially be a simpler regulation system to large reactors. What is the IAEA position on this possibility?
So I am not from nuclear safety and security that deals with regulation. So the question is this about SMRs versus a large facility and regulation? Or did I misunderstand?
I think what Simon's saying in this comment that he and I discuss occasionally is that if you look at a large, at a nuclear program using the standard protocols in the world, then the domestic regulator must have a 100% understanding of the design. And the applicant, not the vendor, but the applicant, the operator, must have 100% understanding of the design. And that therefore implies an enormous amount of engineering being done to relicense something which has been licensed somewhere else. And it's justifiable, when I speak as ESCOM's ex-CNO, it's understandable when you're running 2 by 1,000 megawatts, this is absorb, you can absorb that cost as an overhead for the program. When you want to buy a reactor at 50 megawatts, that kind of overhead is going to kill it. Does that make sense, Melissa? I'm just trying to put the concept down, which says that.
Okay. It's different. There's different strategies for regulations. There's prescriptive, which is more you find in many countries, and then there's one that's more like the English system. And the English regulation system says, you show me that it's going to be safe. It's a different, it's a different strategy. But in either strategy, yes, your regulator has to have an understanding of how it works and if it's safe as well. Of course, your designer and operators have to have an understanding of that it is safe. Yes. So yeah, it's an expensive undertaking, but it's a necessary one. Yes.
Well, that is interesting because you could argue if you apply the same rules to aeroplanes, then to pick on a country unreasonably, but Air Namibia would have to have a full understanding and a full approval domestically of its Boeing 737 from first principles, in which case they wouldn't buy any aircraft. So it's an interesting concept. To what extent do we accept international standards and say this has been approved by somebody and we accept that? To what extent do we have to say no, start from scratch? Interesting concept. I'm not going to go on the line too much. I think we're slightly over time at this point if I look at my schedule. And I don't see any other questions in the question box unless someone else is coming up. So I'm going to pass back, I think, to Minx to close this session off. And thank you very much.
Mr. Nichols, I can just comment one comment on that.
Anyone you want to, yes.
I would agree that there is a rightful comparison between the airline industry and the nuclear power industry. However, I would say it's not regulatory aspects, I would say is how the industry interfaces with publics. For example, I flew from Rome on Monday, and no one, when I boarded the plane, said, "Welcome to the plane. We have not had a crash in the last 10 years." Yes, this is what the industry needs to put forward. Is always the first thing is the safety, because it comes out of the regulatory process, and these are the things that they've done first. But maybe they should start the conversation with the publics about the benefits, yeah. And this is something that they're trying to change, and having the conversation of the impact on climate change, yes, and that renewables are not going to carry the base load, and you do need something there that is dependable and will fill in for when you don't have renewable resource, yeah. And I think that's the conversation with public that they will understand. At the end of the day, my prediction was, it's when the pocketbook of publics is going to speak, they will decide for fission, yeah. Yeah.
Yeah,
Last
agree more.
was personal. Personal, I have to say that was not an agency. I'm not speaking as an agency staff member, but that was my personal opinion.
Well, you see, I have to be more careful because I'm less careful. I did warn you, I'm non-PC. So before I blast the minks, I'm just gonna. But I always get amused. You're quite right. Is that if we said, as when you get to your nuclear discussion, you say, well, the last time we actually killed anyone from nuclear power was probably Chernobyl, and about 60 people died, and that's it. Next question, move on. And the airline industry does not start and say, well, we had an aircraft lock, we had 5 crashes last week and 7 people died, but don't worry, we're safe. We have a different culture entirely. You'll next get me onto linear no threshold, which is my pet hobby horse of the land of insanity in terms of regulation, but let's not go there. So thank you very much, Professor. It was a fascinating cover of those aspects we don't normally look at. I would love to believe that fusion is going to come in my lifetime. I'm not sure I'm convinced at the moment, but we'll see. I think once it becomes a reality, it'll spread very quickly across the world. And with that, I'm going to pass back to Minx to close off for the session. So Minx.
Thank you, Prof. Nichols, and thank you very much, Prof. Denneker, for availing yourself for giving this presentation, and for our attendees for staying on to this very, very interesting presentation. I'd just like to wish all in South Africa tomorrow a happy Freedom Day. Enjoy the long weekend, and thank you for joining us. Have a good day further. Goodbye.
Thank you. Bye-bye.